in 2.5, it's called stacked graphs, which is going from graphs of position versus time to velocity versus time, and then to acceleration versus time, and then backwards from acceleration versus time to velocity versus time and position versus time. And what we'll see is that these graphs are all related. They're all related to each other. So 2.5 stacked graphs. First off, just take a car that's simply sitting at rest, not moving. If the car is not moving, then how does its position change with time? Well, if it started at some position, let's say 0, it wouldn't have changed as it goes through time. And of course, it would have no velocity. That would be 0. And obviously, the acceleration would be 0. So all those versus time would give you 0 acceleration. But now let's take the car that's moving with a constant velocity. So we have a car here moving with constant velocity. That one's at rest. And then this one is moving along at constant velocity. Now that's position versus time. If it started at some position, and since it's constant, that would be changing at a rate going up. Well, what would its velocity be then? Well, we could calculate its velocity, which I'll show you shortly. But right now, we'll just assume that it's some constant velocity, a horizontal line above 0, and moving upwards, but staying at the same velocity throughout. So if it's staying at the same velocity throughout, what happens to acceleration? Well, the acceleration must be 0 if the velocity is not changing. Okay. Now let's change that to a car that is accelerating. And that we assume constant acceleration here. So accelerating car. Now it's speeding up, okay? So since it's speeding up, it covers more and more distance as it goes out. So for the first part of the run, maybe it only covered an increase in distance over that amount of time. But the next part, it moved up more of a distance. So it's got a curve shape to it because it covers more change in space with time. So if it's accelerating, its velocity, which also started at some value, was moving up and increasing as it went because it's accelerating. And that means its acceleration related to time is some non-zero value, but it's constant. For acceleration, we'll always have horizontal lines. If it's not accelerating, the horizontal lines will be at 0. If it is accelerating, it will either be in a positive or decelerating negative in a negative direction. So these graphs tell us something, and we can see that the slopes, let's take a look at the slope on this position versus time graph here. Well, the slope, the change in y over change in x, would be, the y is actually s, and the x is actually t, and this is actually our velocity over that time, our average velocity. So the units, meters per second. So the slope on a position versus time graph, the slope is the velocity. So you could say that with me now. The slope on the position versus time graph is the velocity. Well, let's come over here and take a look at this graph. Velocity versus time. Let's look at the slope there. Change in v over, oops, I went too fast. Change in y over change in x is slope. But the y is change in v, and the x is change in t, and we see that that's the acceleration. So the slope on a velocity versus time graph is the acceleration. You can say it with me now. The slope on a velocity versus time graph is the acceleration. So if we want velocity and we have a position versus time graph, take the slope, you'll get the velocity. If you want acceleration and you have a velocity versus time graph, take the slope on that graph and you'll get acceleration. Okay. So let's look at an example of that. So let's say I had position plotted up versus time, and it'll look like this. I'm getting this plot out here. Oops, I went too far. And then okay, there we go. This is time in seconds. This is position in meters. And this is 6, 12, 18, 24, 30 meters. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. And let's say we want to go to a velocity versus time graph. Well, we have 3 different velocities because we have 3 different slopes. And remember, slope on position versus time gives you the velocity. So the velocity in this region here that velocity we can calculate. So the velocity would equal the slope, which is change in s over change in t, which would be this is the point 3 seconds 30 meters, sorry. And this is the point 0, 0. So it would be 30 meters minus 0 meters over 3 seconds, or 10 meters per second. Now this next one here, well there we have no slope. So v there is just 0 meters per second. And then the next one here, this one, we'll have v is delta s over delta t. We go from 8 seconds, 30 meters per second, to 10 seconds, 0 meters. So it would be 0 meters minus 30 meters over 10 seconds minus 8 seconds, or minus 15 meters per second. Okay? So if we wanted, we have 3 slopes, 3 velocities. And now we could do our velocity versus time graph. Velocity in meters per second. Time in seconds. over the 10 seconds. And the first one was 10 meters per second. So, and that went on for the first 3 seconds. So that was our yellow one. There's that. And then we were at 0 meters per second for the next 5 seconds. Put a good grid on there. And then the last purple one was at minus 15, and that was for 2 seconds. So there's our velocity versus time graph from position. Now, if the position is straight like this, let's think of the acceleration. What's the acceleration? 0, 0, 0, because in each of those three, there's no velocity change. Of course, there's a dramatic one when you go from straight line to straight line, but the true, you'd have to have a curved shape position graph to have an acceleration. Okay, so that's how you can go from velocity to acceleration. Now, you could do the same. If you had a velocity versus time graph, you could go to acceleration. Now, areas under the graph can also give us some information. Okay? Let's go back over here. Let's look at this area here on this graph. I'll put it in purple. The area, okay, of that rectangle would be base times height, which would be t, change in t, times change in v. And of course we know, or times the average velocity, v bar, actually, not change in v, which is average velocity, which is constant here because it stays the same. So that should be average velocity. And of course, that's the same thing as delta S, right? So if you'd like your displacement, take the area under the curve and the x-axis on a velocity versus time graph. So the area under the curve between the x-axis and the line gives you your displacement. Let's look at this one here with acceleration. Well, the area there, oh, I should use capital A, sorry. Capital A would be base times height, which would be t, delta t times average acceleration, which is change in v, isn't it? So if you want your change in velocity, take the area under an acceleration versus time graph to go to velocity, and that will tell you what your change in velocity is. To get change in position or the displacement, you do area on a velocity versus time graph. To get velocity from an area time graph, or from acceleration versus time, you take the area onto the acceleration graph. Okay, so we'll just look at one of those real quick, where we have velocity versus time, and we go to position. All right, we'll set this problem up, and we're going to be going from velocity versus time to position versus time. and we're going to assume that our initial position is 0. And so this can get a little tricky, and I know I was going fast, so we'll do some more problems like this in class to get used to it on how it works. So let's start with our velocity versus time graph, okay? We'll put that here. Now, 2, 3, 4. To 12 meters per second. 1, 2, 3, 4, 3. For the first 3 seconds, the velocity rises up to 12 meters per second. Then it stays flat for the next 4 seconds. Make that green. Then it drops down to 0 for the next 2 seconds. And then over the next 2 seconds, again, we'll bring it out to 11. It goes to a negative 12. Okay? Now, from this velocity versus time graph, we could go down to the acceleration, and there would be 3 of them. There would be a positive acceleration in the red zone, a 0 acceleration in the green zone, and a negative acceleration in the blue zone. Okay? But you know how to get the slopes and do that, so I won't do that here. I'm going to go backwards to get position versus time. And I'm going to assume I'm going to start my position at 0. So my SI, initial position, is equal to 0. We're going to go up from there. We'll have to see how we end up going to get our time 0, we end up at 0. And then we'll see how it increases as we go up. So for the first part here in the red zone, well, I should have done, I'm going to change this to purple. Okay? But in the red area, I have this area that I'm going to calculate. Remember, area under the curve is going to get me, between this and the x-axis, will get me my change in position. So the change in position here is the area, which would be 1/2 base times height, since it's a triangle. The base would be 3 seconds, and the height would be 12 meters per second. And now I can see that the seconds would cancel, leaving meters, and I would have 18-meter change, positive. Okay? So in the next zone, I'm going to change more than that 18. I have a positive again. So in the green zone here, it's that area. And that will be delta S equals base times height, since it's a rectangle. and that would be 1, 2, 3, 4 seconds, with a height of 12 meters per second, which would be 48 meters. And then in the blue zone, we have a triangle again of 1/2 2 seconds times 12 meters per second, which is just 12 meters. And then in the purple zone, I have an area of 1/2 base times height, which is 1/2 2 seconds times the height, which is actually minus 12 meters per second, which gives me minus 12 meters. Okay, so we change from 18 up 48 up 12. So that means 18 plus 48 plus 12 gives us 78. So I got to be able to go up to like 80. So I'll do this. 20 meters, 40, 60, 80. Now I'm going to start at an SI of 0 here. And in the first 3 seconds, I go up a change of 18 meters. So I'll be up at 18 meters by then, right about there. But let's think of the velocity as that goes. The velocity started at 0 and went up. And remember, the slope on position versus time is the velocity. So we have to start out with a horizontal line that trends upward as it goes up to that point. So it's curved, remember. Okay? If it's accelerating, the position graph is a curve instead of a straight line. Then the next one, I go up from 18, I go up 48. And 18 plus 48 is equal to 66. So I'll go up 66 to 66 by 7 seconds, which will bring us up to about there. And now that one has a constant velocity, so that's a straight line to there. Okay? Now in the blue, I'm still going up, and I'm going to go up 12, so 66 plus 12, 78. So 78 will bring me up to here, but I'm going to end up at a velocity of 0, because I can see here, right at this point, that the velocity equals 0 there. So I have to go back down to a horizontal line, so it's going to curve like that, you see? And then, in the next one, I go down 12, so I'm going to go back to 66 over the next 2 seconds. But my slope is going to go, my velocity is going to go from 0 to a negative 12, so it has to curve like that to represent the negative slope. So there's my position versus time graph, and from my velocity versus time graph. And if you can do that, you can do all of topic 2, and you're on your way.